Welcome to lecture 27 of Mechanics of Materials. The last lecture we saw how to derive the general equation for bidirectional bending, that is, when the load is not applied along one of the principal axes of the cross section. We saw how to get the deflections and stresses. In particular, we saw that the expression for stress is given by this expression in here, and the expression for the corresponding deflection along the y and z direction is given in here. Okay, so we also saw that now the neutral axis will not be aligned along with the axis of the problem that you have chosen, but it will be inclined to the axis of the cross section that you have chosen, and that expression is given by the expression given here, tan beta equal to Iyy into mz plus Iyz into my divided by Iyz into mz plus Izz into my. In today's lecture, we will apply these concepts to solve two problems. One is an equal angle loaded about one of its legs like this, and an equal angle loaded about its principal axis, one of the principal axis like that. Okay, so this is what we are going to do in today's lecture. In particular, we are interested in solving the problem wherein you have a simply supported beam subject to a point load in the middle, and this point load is acting along one of the legs in the first problem of the equal angle section. The dimensions of the angle are given here. Each of the leg is 100 mm in length and 10 mm in thickness. Okay. In lecture 25, we saw how to compute the moment of inertia and the center of this cross section. So I am not going to repeat how I am going to compute the center and the moment of inertia of this cross section, but give the end results. Okay. So for this cross section, the YCG is since it is an equal angle cross section, you know that the centroid of Y centroid and Z centroid would be same, and that is equal to 31.2 mm. That is, this distance is YCG and this distance is ZCG. Both of them are 31.2 mm. Okay. Now, similarly, for this cross section, for the oriented axis, Iyy will be equal to Izz, again because it is equal angle, and that will be equal to 2.4 into 10 power 6 millimeter power 4. Okay, and then Iyz is going to be 1.4 into 10 power 6 millimeter power 4 for this orientation of the coordinate system, y and z directions. Okay, so basically these are the section properties of the cross section. Okay, now the first thing we want to find is what is the orientation of the principal axis. Okay, so to find the orientation of the principal axis, phi, we saw in lecture 25, again this is given by 1/2 tan inverse of 2 times Iyz divided by Izz minus Iyy. Okay, since Izz and Iyy are same, this happens to be 45 degrees because tan inverse of infinity is 90 degrees and this happens to be 45 degrees. So the principal axis is oriented like this at the rotation of 45 degrees to this. This will be your U and this will be your V. This angle is 45 degrees, the phi. Okay, so that's the orientation of the principal axis. Okay, now for this loading, for this orientation of the coordinate system, you know that the moment that is produced is a mz moment, and you can find what is the support reaction. The support reactions are going to be, for the simply supported beam, the support reactions are going to be, okay, for the simply supported beam, the support reactions are going to be P by 2. I am not going to go into derivation of this. The load is acting at the center, so you take a moment about one of the edges, one of the supports, say at A, you get that from the moment balance you will get the reaction at B to be P by 2, and from the vertical force equilibrium then the reaction at A has to be P by 2. The same thing can be inferred from the symmetry of the problem. Okay, so this is a free body diagram of this beam, and hence the variation of mz moment, with x is given by P by 2 into x for 0 less than x less than L by 2, and P by 2 into L minus x for regions L by 2 less than x less than L. Okay, here x is measured from the end A, x is measured from here, this is x, any section here will be x. So any section on this segment, section here will have a distance from this end as L minus x. So basically now for a section greater than L by 2, it will be P by 2 into L minus x will be the moment that comes in at that section point. Okay, by now you should be familiar with writing this equation. So you have done that thrice in this course, so you have to be conversant in writing these equations. Okay, so mz is this. Now going back to our expression for the deflections, you will find that my is 0 for this, mz is this, and my is 0 because the load is acting along the y direction. So my is 0. Okay, for this case you will find that E times d square delta y by dx square is given by Iyy divided by Iyy Izz minus Iyz squared into mz. My is 0, so I have used this fact and put the bending moment equations into this equation in here. Okay, I put the bending moment mz and my into the equation in here, and hence we got that. This I will write it as k1 times mz, where k1 for our cross section is 0.63, where k1 for our cross section is 0.63. Okay, similarly E times d square delta z by dx square from the equation above will be minus Iyz divided by Iyy Izz minus Iyz squared times mz. This will write it as k2 times mz, where k2 is 0.37 for our cross section. Okay, where k2 is 0.37 for our cross section. Okay, now proceeding further, we got d square delta y and d square delta z dx square. So we want to find the deflection and the stresses. So the deflection is given by, to get the deflection, d delta y by dx is given by, I substitute for mz into this equation, so that will be p x square by 4 plus c1 for 0 less than x less than L by 2 p L minus x square by 4 minus plus c2 for L by 2 less than x less than L. Similarly, E d delta z by dx would be, there should be a negative sign there, minus k to mz, because there is a negative sign in there. That will be minus k2 p x square by 4 plus d1 for 0 less than x less than L by 2 minus k2 p L minus x whole square by 4. Negative sign for the differentiation makes it positive, plus d2 for 0 less than, for L by 2 less than x less than L. Okay, now integrating this once more, I get E times delta y to be k1 p x cube by 12 plus c1x plus c3 0 less than x less than L by 2 minus k1 p L minus x cube by 12. I have negative sign there coming in because of the integration, so that will become positive. I write c2x as minus c2 to L minus x plus c4 for convenience, that you will see later shortly now. Okay, this is same as c2x, right? I added c to L, so c4 would be c4 minus c to L will adjust itself, that is a constant. Okay, similarly E times delta z is given by minus k2 p x cube by 12 plus d1x plus d3 for 0 less than x less than L by 2 minus k2 p to L minus x cube by 12 plus, I do the same trick here, minus d2 into L minus x plus d4 for L by 2 less than x less than L. Okay, next I have to find the constant c1 to c4 and d1 to d4, for which I apply the boundary conditions. Simply support boundary condition means delta y at x equal to 0 is equal to delta y at x equal to L, that has to be equal to 0. Same thing in z direction, I do not allow displacement in y or z, so delta z at x equal to 0 and x equal to L has to be 0. Here I am assuming it is simply supported in both y and z direction, but it is not always necessary. It can happen that it can be simply supported in y and fixed in z, or vice versa, or fixed in both, so that depends upon the problem at hand. Okay, so this is 0. So these conditions will imply that delta y at x equal to 0 implies c3 is 0, and delta y at x equal to L equal to 0 would imply c4 is 0. Similarly here delta z at x equal to 0 implies d3 is 0, and delta z at x equal to L equal to 0 implies d4 is equal to 0. Okay, so now we have to find constant c1 and c2, that comes from the continuity condition. The first continuity condition that will enforce is delta y at x equal to L by 2 minus should be equal to delta y at x equal to L by 2 plus. So what does this mean? This means k1 p L cube by 12 into 8 plus c1 into L by 2, c3 is 0, must be equal to k1 into p L cube by 12 into 8 minus c2 into L by 2. Okay, this implies c1 is equal to minus c2. Okay, similarly here delta z at x equal to L by 2 minus must be equal to delta z at x equal to L by 2 plus, this is the continuity condition at L by 2. This will imply minus k2 into pl cube by 12 into 8 plus d1 into L by 2 must be equal to minus k2 into p into L cube by 12 into 8 minus d2 to L by 2. This again implies d1 must be equal to minus d2. Okay. Now moving forward, we want to apply continuity condition on d delta y by dx. Okay. So continuity condition, second continuity condition that we will be using is d delta y by dx at x equal to L by 2 minus must be equal to d delta y by dx at x equal to L by 2 plus. Okay. So this condition will tell us that from the equation here, it will give us, this implies k1 into pl square by 16 plus c1 must be equal to minus k1 p L square by 16 plus c2. Okay. Already you have c1 equal to minus c2. So this will imply that this implies 2c1 is minus k1 pl square by 16 into 2. Okay. Or c1 is minus k1 pl square by 16. Okay. Similarly, applying the condition here, d delta z by dy, d delta z by dx at x equal to L by 2 minus must be equal to d delta z by dx at x equal to L by 2 plus, you will get minus k2 pl square by 16 plus d1 must be equal to k2 pl square by 16 plus d2. Here the sign differs because there is a negative sign in here. You can see that this has a differing sign from what you add here. Okay, hence the sign will differ. Okay. Okay, so this implies along with the condition that and you add a condition d1 is equal to minus d2 from the continuity of the displacement. From here you got that condition d1 equal to minus d2. Here you got the condition d1 equal to minus d2. These two conditions together will tell you that d1 is k2 pl square by 16. Okay. Now substituting all these values of constants into the deflection equation, you have E times delta y to be given by k1 pl cube by 48 into 4 x by L whole cube minus 3 x by L in the region 0 less than x less than L by 2, and I have k1 pl cube by 48 4 into 1 minus x by L the whole cube minus 3 into 1 minus x by L in the region L by 2 less than x less than L. Okay. Similarly, E times delta z is given by minus k2 p L cube by 48 4 into x by L the whole cube minus 3 into x by L in the region 0 less than x less than L by 2, and minus k2 pl cube by 48 into 4 into x by L whole cube minus 3 into 1 minus x by L in the region L by 2 less than x less than L. Okay. Next we are interested in finding what is E delta y at x equal to L by 2. This you will find is minus k1 p, so you will find is minus k1p L cube by 48. Okay, and similarly here you will find that E of delta z at x equal to L by 2 is k2p L cube by 48. Okay, because it is 1 by 2 minus 3 by 2. 1 by 2 minus 3 by 2 is minus 1. So, this one with the negative sign becomes positive for delta z, and it is negative for delta y because there is no negative sign in front of delta y. Okay. So, what does this mean? Let us interpret this result with respect to the cross section. Okay. Let us go back to the cross section. What deflection we got was negative displacement in y and positive displacement in z, which means the CG from here will move to a point from the CG from here moves to a point somewhere here, wherein this displacement is delta y, absolute value of delta y, and this displacement is absolute value of delta z. Okay, that is the displacement. So, what it does is it moves down and it moves in the z direction. Okay, in the z direction it moves down and out of plane, out of the board. Okay, whiteboard. Okay, so that's what it happens. Okay, so now this is one way of solving this problem. There's another way of solving this problem wherein I can resolve this loads into the principal axis. Okay, and I can repeat the same thing. Then what I will get is I will get the deflection along u and v directions. I have to then resolve that deflection along u and v directions to y and z direction. Okay. Now what we are going to do is we are going to resolve these forces along the principal directions. So this P, when resolved along y, u and v would be, and resolved along u and v, it would be along v, this is going to be p by root 2 because it's 45 degree rotation, because the rotation is 45 degrees. That's what we saw for the principal axis from the given axis. So this will be p by root 2, and along the u is going to be p by root 2. Okay, so you will have moments mu and mv. Mu is given by p by root 2 into x for 0 less than x less than L by 2, and it will be given by p by root 2 into L minus x for 0 less than for x L by 2 less than x less than L. Okay. Similarly, mv moment given by p by root 2 into x again 0 less than x less than L by 2 minus p by root 2 into L minus x for L by 2 less than x less than L. Now let's see how I got the mu moment. Mu moment would be the load along u direction, load along v direction, okay, multiplied by the lever arm along the x direction. Okay, that will give me mu moment. So I have a load, I have this angle cross section in which the load is acting like this. So this load is going to produce a mu moment like this. Okay, the lever arm is along x, there is a load acting like this, so there will be a moment mu produced because of that load. Okay, and there will be a negative moment, and mv moment is the moment produced due to the load acting along u due to a lever arm along x direction. Okay, that will be the mv moment. Okay, so that will be given by this expression in here. Okay, so that is the mv moment there. Okay, now you know that IUV is 0 since it is the principal axis, and hence E times d square delta E square delta u by dx square would be given by mv divided by IVV. Okay, mv divided by IVV. Okay, now we have to find IUU and IVV. Okay, we will do that shortly. and similarly E times d square delta V by dx square is given by mu divided by I UU, mu divided by IUU, mu divided by IUU. Okay. Now I know that I can use most circle equations to transform my to find IUU and IVV. IXX and IZZ and IZZ and IYY were same for this cross section. So the expression for IUU would become IYY plus IZZ by 2 minus IYZ into sine 2 phi, which is sine 2 times 45 degrees. So it will be 2 times 90 degrees. Okay, that is 1. So this will IYY and IZZ are same, so I didn't have a cos 2 phi term. Okay, so now this boils down to 1 into 10 power 6 mm power 4. Okay, similarly IVV is given by IYY plus IZZ by 2 plus IYZ into sine 90 degrees. So this will be 3.8 into 10 power 6 millimeter power 4. Okay. Now I have to repeat the steps that I did for integrating the moments, similar to what I did in the previous case, and find delta U and delta V, and you can show then that delta U would be given by delta Y that we found in the previous expression plus delta Z by root 2, and delta V would be given by minus delta Y plus delta Z by root 2. Okay. Now I will leave this as an exercise for you to work it out and show. Okay. Now moving on to the stress expression, the stress sigma xx now would be given by, from the equation that we had before, from this expression you will get the stress to be given by y minus y naught into IYY divided by IYY into IZZ minus IYZ squared into MZ, the negative sign in here, plus Z minus Z naught into IYZ divided by IYY IZZ minus IYZ squared MZ. Okay, we got the expression for MZ. So you know how the axial stress will vary along the axis of the beam, and there is a variation along the cross section of the beam, in the cross section of the beam. Okay, of interest is the neutral axis, that is the axis about which sigma xx is 0. So you will find that the orientation of the neutral axis tan beta is given by z minus z naught by y minus y naught, which is nothing but I YY divided by I YZ, and this is 2.4 divided by 1.4. This will imply that beta, if you do the inverse of tan, it will be 59.7 degrees. 59.7 degrees. Okay. So now if you look at the angle section, the principal axis is oriented at 45 degrees. This is 45 degrees, but the neutral axis is oriented at 59.7 degrees. Okay, that is, the neutral axis is oriented in some line like that. This is the neutral axis. And its orientation from the vertical is 59.7 degrees. So now what happens? Below the neutral axis, you have applied a load like this, and which points will be in tension and compression is the next thing that we want to see. Okay, so it's convenient to see that when you resolve the forces into the principal axis orientations. Okay, so basically when I apply a load like this, we are interested in finding what are the nature of stresses at points P, at points L, M and N. Okay, to find the nature of stress at M, when I resolve the load along the principal axis direction, you find that the P by root 2 acting along V will produce compression at M, will produce tension at M, and the load acting along the U direction, P by root 2 load acting along U direction, that will be the neutral axis, so it won't produce any tension at M. Okay, so at M it will be T plus 0. Okay, similarly at L, the load acting along V will produce compression. Okay, the load acting along the direction of the principal direction V will produce compression. Load acting along the direction of U will produce, this is the P by root 2 load acting like this, that's a P by root 2 load acting like that. So that is going to also produce compression at L, so there will be compression and compression at L, whereas at N the load acting along V produces compression because it is above the U axis, and load acting along U will produce tension because it is below the V axis. Okay, it will produce tension there. So basically now you will find that M would be in tension, L would be in compression, and N can be in tension or compression depending upon which is dominating, because it is a combination of a tensile stress and a compressive stress. Okay, that depends how the orientation of the neutral axis is, what the orientation of the neutral axis is. Okay, so this kind of analysis you should be able to do to quickly tell whether a given point will be in tension or compression due to bending stresses. Okay,